So my name is Dominic. Thank you very much for the introduction. That's exactly what I've come here to talk about, is open source spectrum monitoring. I work for a company called Great Scott Gadgets. So this is me. In case anyone can't see my face, this is what I look like. I work on open source hardware and software. I mostly work on things like Ubertooth, which is a Bluetooth sniffing tool, GreatFet, which is a hardware hacking tool we're working on at the moment, and HackRF, which is this software-defined radio peripheral that I think many of you would have heard of, and I think they may have mentioned in the previous talk, but I'm not sure. And I wrote a little site called fcc.io, which is not covered in this slide deck at all, but is something that I might try and mention it once or twice about open source intelligence when it comes to radio devices. So here are some of the products we make, and specifically today I'm going to be using HackRF, which is this big one in the middle. It's a software-defined radio. It has a kind of 1 megahertz to 6 gigahertz tuning range. It grabs 20 megahertz of bandwidth, and it's all open source, including the hardware and the firmware. And what we're going to do here is we've written some custom firmware to do some interesting things that you can go and play with. So what is spectrum monitoring? Well, as the introduction said, someone plants a device within your organization. You want to be able to look for it. You want to be able to find it. You want to know it's there. You want to have a really good idea of whether or not those devices have been put there. What are people in your organization bringing in? Sometimes you want to specifically locate them, which is not necessarily the direct theme of this today, but is certainly possible using some of these techniques. And what we want to do is monitor the spectrum around us for new and different things. Now, if you work in an environment where you have a network, you might hopefully monitor your network for people adding devices to your network. You monitor your Wi-Fi for people connecting to your Wi-Fi. So are you doing anything to monitor the fact that someone might bring in a transmitter that exfiltrates data over unlicensed 900 megahertz or 433 bands? Do you know if people are doing that? Have you got any idea whether you would even know if someone did that and brought that sort of capability into your organization? And potentially, do you care? So, I mean, the people who should care are large organizations. It's just part of monitoring your perimeter, monitoring your security. There are companies that will sell you solutions to do this. This is not a brand new concept or anything. In fact, the previous speakers work for Bastille, and I believe that's part of their offering. And you know, there are all sorts of different ways to do this. What we're looking at now are some of the available tools to go and look at the spectrum around you and your organization. We use it specifically for reverse engineering within Great Scott Gadgets. We like doing wireless reverse engineering and hardware radio hacking. And so we'll pick up a device and we'll have this little piece of IoT gear in front of us, and we'll switch it on. And then the first question is, well, what protocol is it talking? What's it communicating over? And you can not always trust the box. I mean, we have seen electric skateboards that had a controller, and the controller had a switch on it that said Bluetooth and Wi-Fi. And when you switched it into the Bluetooth mode, it was definitely not Bluetooth. When you switched into the Wi-Fi mode, it was Bluetooth. And the Bluetooth mode was some proprietary 2.4 gigahertz, and we had no idea. This is Richo, Healy, and Mike Ryan's work from a couple of years ago. They did a great DEF CON talk on it. But they were baffled by this for a short time before they pulled out a HackRF and started looking at the spectrum and saying, well, it's probably 2.4 gigahertz if they've claimed to be Wi-Fi and Bluetooth. So maybe we look there and we see, and like they were flicking the switch backwards and forwards, and it's definitely something going on. And then Mike Ryan looks at the screen and goes, that looks like Bluetooth. And so then he was able to start decoding it and things like that. But that took the fact that Mike Ryan had the ability to look at the screen and visually identify Bluetooth from an FFT, which is pretty much what I'm going to show you today, that I also have that ability. But hopefully we're moving towards a place where other people have that ability, or automated tools do. And that's really the focus of where we want to get to, starting from this baseline. So the other people are, right at the bottom here, are radio operators. Can we just have a quick show of hands? Has anyone got their amateur radio license in the room? So a handful of people, okay. So I'm reliably informed that if you start transmitting on a channel that you shouldn't be, the amateur radio operators will be the first people to track you down. Significantly before the FCC or Ofcom or whoever your governing body is, amateur radio operators are fantastic at finding interferers quickly, and I think they get a kick out of this kind of ability to monitor wide bands of spectrum, because they can look at who is transmitting and maybe whether or not they should be transmitting and obeying the rules. So the way we're going to do this is really 3 steps. We're going to take a software-defined radio, we're going to perform an FFT, and then we're going to plot the output of that FFT. This is not particularly new. RTL, has anyone got one of these RTL SDR dongles, the little TV tuners? Excellent. There's a tool called RTL Power, which will pretty much do this for you. You combine that with a Python script called heatmap, and it generates images for you that show you a broad kind of sweep of spectrum and where the power is. And as I said previously, this isn't new. RTL Power and heatmap, which I'll show you in a second, but also this is Satmap by Adam Laurie. Now what Adam did for this was he had a steerable satellite dish mounted on the roof of a building, and he steered the dish slightly, tuned the full sweep of the frequency range of his receiver, looking for power, and then tuned the dish slightly again. So this plot at the bottom of the screen here is west to east, tuning across the sky, and the frequency is between 10.7 gigahertz and 13 gigahertz, I think. Those are all up in satellite ranges, I believe. And so he looked for where there was power on there, and then he made this map of the sky, which he calls Satmap or Sky Map, depending on which page you look at. And some of them are interesting. You've got these big transmitters, which are on a bunch of different frequencies simultaneously. And they're probably your communication satellites, your TV satellites. But every now and again, you get something that's just, like just up here. This thing, very narrow transmitter, very narrow amount of channels on there. So someone's gone to the effort and the cost of putting up a satellite just to communicate on that frequency. So someone with money is communicating via their own satellite because they don't want to use existing communications technologies. So that might be an interesting one to go look at. So this morning I did this scan. This represents 1 hour 53 minutes, which heatmap helpfully writes all over your image over here. I should have remembered to turn that off before outputting the image. But this is a scan of what's going on, sweeping from pretty close to 0 megahertz up to 1.7 gigahertz, which is the tuning range of this little RTL SDR dongle. And this is, all it does is it tunes to a frequency, takes a sample, runs an FFT to see where the power is, tunes to the next one, to the next one, to the next one, and just sweeps across this spectrum. And then heatmap ingests this data and spits out an image. And this gives you a really good idea of what's around you. So we can see there are a lot of powerful transmitters that are pretty constant. Some of those will be phone transmissions. There'll be radio towers. There'll be down here around 100 megahertz. We'll have broadcast FM. We'll probably have a couple of GSM networks and various other things like that. But you can also see, and again I'll try and show you, up here we've got some very, very short, to be clear, it's frequency on the x-axis, time on the y-axis. We've got some very, very short transmissions here and here and here. So they're much more likely to be, especially around 900 megahertz, unlicensed things. 900 megahertz unlicensed things shouldn't be being used in Europe, but in the same frequency band. But they are likely to be small devices. There's a fair chance from this that I could tell when the hotel staff came into my room to clean it, especially if I were able to get up to 2.4 gigahertz. I'd probably spot their phone and things like that when they entered the room. Now, we can do the same thing with HackRF, but because we wanted to get good performance out of HackRF, what we did is wrote our own custom firmware for it. Say custom, we control the firmware anyway. We wrote a modified firmware for it that sweeps and does that retuning in firmware. So it retunes, takes a sample, retunes, takes a sample, retunes, takes a sample, and dumps all these back to the host. And this means we don't have the round trip time between the host and the over USB. We don't have that latency, so we can retune much more quickly. And in fact, we have to use a modified version of heat map, because heat map assumes that when sweeping from the left to the right of your frequency range, it can use timestamps with a granularity of 1 second. And we're able to sweep our frequency range, which is 0 megahertz to 6 gigahertz, in about 0.75 of a second. So we need a microsecond or around that timestamp resolution. So I ran at the same time as this RTL power heat map, I ran one for HackRF. Now, we have a slight problem with resolution and the screen, because this is the same map. So this is the same width, but significantly more resolution in the vertical axis. This is a 62 meg PNG, so I apologize for anyone who downloads the slides, because it's in here twice. And as you can see, this isn't the same width, sorry, I lied. This is 6 gigahertz wide, so this is more than 3 times as wide as the previous image, and it's significantly higher because we're getting that much more data. Now, I have clearly slightly screwed up my my power threshold on this because it looks a little bit washed out. But you'll spot that there's an awful lot of noise, awful lot more power here, if I hadn't blurred the whole thing. There's a reasonable amount of power here. We still have some interesting things down here. This is very spotty, which you cannot see unless you're as close as I am. But we have so much data, you need to get in there and look at it. So we're able to receive 6 gigahertz of data in 6 gigahertz wide bandwidth. We're able to sweep through the power on that in 0.75 seconds. So we have a lot more information to play with. But it's kind of more interesting, potentially, to look at this stuff in real time. I took that sweep over the course of 2 hours. I then spent the rest of the day trying to coax heat map into producing an image from it, which I clearly failed to do at reasonable power levels. Turns out it's really important that you remember decibels are often negative, because otherwise, if you think they're positive, everything's out of range. So what I'm going to show you now is Q spectrum analyzer, which should show up. Excellent. And if I go into my settings and use HackRF sweep, 20 megahertz, that's fine. So this is going to scan from 1 megahertz to 6 gigahertz, and hopefully should give us some output on the screen. Well, it's not great, is it? So I was hoping we'd see something more spiky there. But essentially, this is giving us real-time data. I've screwed something up slightly with the way these FFTs are calculated. But this should be showing us real-time data for that sweep, and every line on this waterfall is a sweep, and we're getting it about just shy of once a second. And so we can start to pick out things in real time and see when they're actually transmitting and when they're not, and it would be great if this data looked good. So I'm clearly not doing the FFT properly, but that's okay, because hopefully I'm going to be able to show another version of the same thing. To be clear, this is that original image, and we can zoom way in. No, we can't, because let down by my tools, which obviously is my fault. But okay, so that's fine. Q spectrum analyzer is actually a relatively good way of looking at this, but as it turns out, I can't work it. But it might also be interesting to do to use some of the tools we're used to. So if anyone's played with software-defined radio before, you've probably used GNU Radio Companion. You're used to various visualization tools that are in there, and it might be nice to get data into those. And previously, what we did is we tuned to a frequency, took some samples, performed an FFT, which gave us that frequency to power map that we could plot. Now, the FFT is a reversible function, so we can convert the output of that power map back into samples. The question is, why would we want to do this? When you're receiving radio, you bring the radio that you're receiving down to baseband, perform the FFT, and get a series of power values. But what we've got is 6 gigahertz wide of radio, and we get lots of small bursts of samples that we've got down at baseband. So what the inverse FFT lets us do is take those FFTs and plot them next to each other as if we have a 6 gigahertz wide FFT, and then we run the inverse FFT, and instead of running it on small chunks of data lots of times, we run it on one big piece of data once, and we get back data that is 6 gigahertz wide. Is everyone with me so far? Is anyone with me so far? Yeah, vaguely. There are some hands up in the front from people who are slightly unsure that I know what I'm talking about. But this allows us to view the data in, there we go, in some of the tools that we already know and love. So it takes a little while to pre-calculate some things. We've got to set up some buffers for the inverse FFT. Hopefully it didn't just die. So it takes a little while to just start this up. You can't particularly see what I just typed, but here we go. And so what we should be able to see now is this is, again, doing the same thing, and it's sweeping over 6 gigahertz wide, and it's performing an FFT over every 500 kilohertz, and then plotting that using GR phosphor. So you'll probably be used to this if you've used software-defined radio in the past couple of years to look for signals. This will show you, this is very good at showing you transient signals, and we can see the 2.4 gigahertz section again. Again, like we're looking at 6 gigahertz wide here. We've got the 0 point in the middle. So negative 0.6, that's the 2.4 gigahertz spectrum, and various other things. Down here, we're pretty close to DC, so we get a bit of distortion. And we'll see, I'm not sure what's at negative 2.4. Any suggestions from the front row? What's down at, what is that, negative, that's about 900 megahertz, I guess. So that's probably where that spike is. I have no idea what around me is transmitting 900 megahertz, potentially the microphone. And so we're able to view the data that we had captured as disparate wide sweeps in kind of almost real time in tools we know, and we're able to identify transient signals this way. So if I run the same thing again, but I limit my frequency range, so my sample rate is it's 100 megahertz wide now. This is the 2.4 gigahertz band, and it's sweeping the whole thing in a much significantly quicker than that, because it only has to do 5 hops to get the whole thing at 20 megahertz chunk. So you can see there are 2 large Wi-Fi networks going on. There's a third which is kind of quieter. If I pull out my phone, hopefully I should be able to fire up Bluetooth and have it scan, and you'll see it suddenly spits data all over the spectrum. But the interesting thing here is we're getting the vast majority of that data, as opposed to generally just pointing at a chunk of the 2.4 gigahertz band and seeing what comes in. We're getting these broad packets all over the place. So you can tell quite how much. It's actually very difficult to see on this screen with the lights on. But if you see the red line up at the top here, you can see those very transient spikes are showing up, and they should be showing up in the waterfall as well. And they are very short Bluetooth packets where it's searching for another device when my phone is trying to connect to, I don't know, a speaker or something that it's seen before. And so it's able to, it puts those across the whole bandwidth. So you can see them in the waterfall now that I've restarted the scan. Can anyone actually see that, or is it completely washed? Okay. I'm struggling from this angle to see it, but I can see it on my screen, which is not helpful to you. But those bursts are very quick, and they're transient unless you're looking in the right place. I mean, 10 years ago when I was trying to build the first, or our first software-defined radio implementation for Bluetooth, I had to point to at the time, 8 megahertz wide chunk of bandwidth and just hope that Bluetooth strolled past at some point. Whereas with this, I'm able to go and look at where it is in the in the spectrum. And like for Bluetooth, it's all over the place, so it's probably not such a big deal. But last year, we were trying to reverse engineer some little wireless quadcopters that were 2.4 gigahertz transmitters, and they claimed to be 2.4 gigahertz frequency hopping, and we were able to use techniques like this to go and look at the whole band and work out where they were hopping to and which channels they were on, and so on and so forth, because we were able to monitor a much wider section of the band. And so for this, if you're in charge of looking at the radio transmissions around an organization, if you're concerned about people bringing in 2.4 gigahertz transmitters that are IoT devices that they are not supposed to be bringing in, you can monitor this and you know that these are your two valid Wi-Fi networks. So if a third one pops up somewhere, you might have to start asking questions. If you see things, just a narrowband transmitter at one point in the frequency range at some point, there's a fair chance that it's not Wi-Fi, it's not Bluetooth, so it's possibly some other 2.4 gigahertz transmitter that someone's brought into your organization. And like maybe it's someone bringing in a little quadcopter to play with, or maybe it's someone exfiltrating all your company's data. But I'd want to know which. So that is inverse FFTs, and that's pretty close to the end of what I actually have to show. Oh yeah, let's try looking at that in InIn Spectrum. So there's a slight problem with InIn Spectrum and doing this technique, which is InIn Spectrum doesn't support greater than 32 bits of frequency range, so I have to lie to it and claim that I'm a much narrower signal than I am, because otherwise it doesn't understand 6 gigahertz of bandwidth. This is the wide scan that I showed you earlier. This is part of the a subset of the really wide sweep from earlier. So you can see my power levels are kind of off a little bit, but again, we can go in and we can look at some of these packets, and you can see there's something transmitting here, which is very spotty. You can see a reflected image here, which is probably an alias of the same thing. And hopefully I should be able to zoom in on some of these things. I was really hoping I'd be able to see more detail on these, but apparently not. So in some cases, what you'll be able to do is use InIn Spectrum to go and look at and visually identify things like the modulation on these. Things like, let me try and alter my power level. So this is not a working demo. I'm sorry about that. I was really hoping it would be. So sometimes you're able to visually, from this, look at an image and in Spectrum, and you can literally look at something and you say, hey, it's on this frequency, and I see it's on this frequency, and the one next, it's switching between the two. It's probably frequency shift keying. If you see that it's a fairly dense block of power across a wide band of frequencies, it's quite possibly something like OFDM that just dumps a fairly solid, well-edged block of power across a number of frequencies. Let me try a different file and see if we get any better luck. Otherwise, I will go on to wrapping up. Well, that looks basically the same, doesn't it? This is the 2.4 gigahertz spectrum earlier today. And the problem with doing 2.4 gigahertz at HackerCon is it's basically all power. So, I mean, if everyone could have just agreed to turn off all of their devices earlier today for half an hour, it would have been great. But sadly, I don't think I'm going to be able to show this in InIn Spectrum properly. But maybe I will try and capture a file in my hotel room later and show it to people offline tomorrow. So the idea there is we can we can visually pick out packets and data transmission types and look at what kind of radios might be transmitting, and you can get a fairly good idea for what's transmitting, what type of device it is from the type of radio connection it uses. Quite often there's an awful lot of low power things that will use 2FSK in ISM bands. If you go and look at the appropriate bands, you'll see things like GSM and so on and so forth. So we'd like to, what this presentation is about is trying to show which tools exist and where we'd like to take them next. So that's what I'd like to talk about for just another minute or two. which is we would like to be able to have the capture and the visualization and the analysis all in one tool. We'd like to build an open source tool, preferably, that will allow us to receive that 60 gigahertz of bandwidth, and then when we want to, drill down into, we identify a signal that looks interesting or novel or different, and we can drill down into it and go and take a look at what kind of modulation is it using. Let's do a spectrum plot to see if we can tell what kind of modulation it's using. Let's try and decode it in some way. Let's try and take a capture and dump it out to something like InIn Spectrum, where we can start playing around with processing it, filtering it, demodulating it, so on and so forth. The other thing is we've recently been experimenting with an antenna switching board for HackRF that will allow us to switch up to 4 antennas on the front end of it from the firmware, which means we'll be able to perform pseudo-Doppler experiments with using the same sort of techniques. And if we're able to synchronize the switching of the antennas with the dumping of the buffers back to the host, we'll be able to perform direction finding at the same time as sweeping that whole band. So while you'd lose some performance across the band, you'd be able to gain some information about the direction of the signal. So that is on our to-do list. There are 3 of those boards at the moment. One's in Scotland and one's in South Africa, and the other one's on my desk, and all 3 of us need to get on with doing some work with them. So I just want to thank everyone at Great Scott Gadgets who, unfortunately, I told about the stream, so they're watching now. But thanks to Mike Taylor and Elizabeth. Also Mike Walters, who originally came up with some of the concept for HackRF Sweep. He had a really cool project at EMF Camp last year where he plotted the 6 gigahertz of bandwidth using UV lasers on a piece of glow-in-the-dark material. So you got that onion skin fading effect naturally as it responded to the UV light, which is kind of cool. So thank you to him, thank you to all his hard work, and Mike and everyone else. These are probably the 2 most interesting URLs for this. One is HackRF, where our firmware changes are and all that sort of thing. The other is Spectrum Analyzer, which does actually give you a really interesting view of the spectrum. I've clearly misconfigured mine at some point while experimenting over the past couple of days. But you can use either of those. If you want to use heat map with HackRF Sweep, at the moment you have to use a modified version that we built, but we're hoping to get that pull request pushed upstream this week. And I will take any questions because I have 2 minutes left.
So you showed the heat map, the spectrum for using the RTL SDR, right? Mm-hmm. There was a gap in between. Is it due to the some RTL SDRs having a gap in their frequency range, or is it because of?
I mean, this is a really. You mean this section here? Yeah. It's a really big patch to not have anything in it, I will admit. There are a couple of little things in it. I honestly don't know. I literally took the RTL SDR out of the packet this morning for the first time, so I have no idea if this one has gaps in its frequency range that are causing that problem. But I suspect it's quite a quiet band as it is. Can anyone think of anything between 1 gigahertz and 1.4 that I would see in this hotel? Front row, I'm looking at you. No. It might just be quiet. But there is definitely, if you get up close to it, some transmissions in there. So I'm not entirely sure whether the gaps in receive are on this radio or if there are any. So I couldn't tell you. I'm sorry.
Thanks.
Yeah, Mark.
So I'm just curious, when the HackRF is sweeping, like what's the duty cycle at any one given frequency that it would see?
So what we do is most of the we can increase the duty cycle based on how much data we want to capture, but reasonably what we do is we tune to a frequency. We're pulling back data at 40 megahertz. Let me try that again. We're pulling back data at 480 megabits normally, and that is made up of 16K buffers. So if you can do the maths to work out how long a buffer lasts, what we do is we tune, we wait for 2 buffers in length, which is a very short time, in order to allow the tuning to settle, and then we just capture one buffer, and we're literally operating on the last n number of samples of that buffer, and that buffer is, the n in that case is the width of our FFT.
Yeah, thank you.
No worries.
Okay, if there's no more question, that I would like to close the COMMSEC for today. Thank you all for joining and attending. I've been asked also to tell you, if you're going to leave now, if you're not staying anymore, but if you're going on your way, that you shouldn't go through the main entrance, but look, and you'll be given directions downstairs where you can exit. So please follow them. Thank you all for being here, and see you again either tomorrow or next time.